So let's say we want to find the vector equation of the plane in parametric form. How do we come up with the parametric form for the vector equation? Okay, so suppose you want to define the plane. The first thing we need to do, we need a point on the plane, right? So if we suppose we just have a point on the plane here, let's say this point is A. Say this point is A, right? Then reference to the origin, right, there'll be another O. So this will be the direction position vector A, alright? And then it's parallel to 2. So I mean, stay on this plane, right? Okay, first we need to fix point, and you want to describe, say, a point here. Maybe just another point, say R. We call it X, Y, Z. How do we describe this point? So you know that if we use a parallelogram law of addition, right? If, for example, this point A, right, and this point R, say it lies in a parallelogram law, and if I want to describe this point, right, what I can do is I can use two vectors. Maybe say the first vector, I call it M1, the first direction vector, and I can use perhaps another direction vector. Maybe I will call this M2. Maybe M2. Okay, and using the parallelogram law of addition, you see I can actually define, okay, this plane. Alright, what's the parallelogram law? Just quickly recall. Parallelogram law of addition is, you know, example, this M1, this is M2, right? Then what is this? This vector here will just be M1 plus M2. Okay, so parallelogram law of addition can actually help us to find, so-called define any point on the plane, okay, using the two direction vectors M1 and M2. Okay, so similarly, let's just take another example. If I were to use maybe another point, maybe it could even be somewhere, let's say here. Alright, and similarly, this can also be defined. If I were to quickly form another parallelogram, maybe this is another scalar multiple of M1. This could be another like M lambda M1. Okay, and this will be another multiple of M2. Maybe M2, maybe mu of M2. And then using this parallelogram law of addition again, you can see that I can easily define another vector, right? So very quickly, right, it means that actually to effectively define a plane of points, right? Effectively, if you want to define a plane of points, what we really need, right, is we really need one position vector on the plane, as well as one direction vector, two dimension vector. Alright, and we can actually define all points on the plane. Okay, so with that, right, the vector equation of plane P, the vector equation, very quickly, the vector equation okay, so the vector equation of plane P in parametric form will be a position vector A, which lies on the plane, plus a scalar multiple of M1 plus a scalar multiple of M2, where lambda and mu are all member of real numbers. Okay, and here will be R, and R, as you know, this would be X, Y, Z, any X at a point, any on the plane, and recall that this is a position vector of a point on the plane, and these two M1 and M2 are two non-parallel vectors. Okay, they need not lie on the plane because direction vectors, they lie freely in space, they need not lie on the plane. Okay.